Yeah, hello everyone. So here we are going to continue the topic, the state space representation that we have previously discussed a little bit. Okay, so the idea here is from the idea of modern control, where we now go toward greater complexity, due mainly to the requirement of complex tasks and good accuracy. And the complex systems here may have multiple inputs and multiple outputs, or MIMO, and maybe time varying. And for modern control theory, which is a new approach to the analysis and design of complex control systems. Yeah, this has been developed actually quite some time already, since around 1960, and we are now using the approach based on the concept of state. So we no longer use transfer functions. We still do sometimes, but it's not the main approach that we use. Instead, now we use the concept of state. So for the modern control theory, this one is now applicable to multiple input and multiple output, which may be linear or non-linear, time invariant or time varying. On the other hand, the conventional control here applicable only to linear time invariant, single input, single output system. So usually for the transfer function, we focus only on the LTI, single input and single output systems. And for the modern control theory, we now use the time domain approach and frequency domain approach, while the conventional control theory mostly uses complex frequency domain approach. So, yeah, like the one in transfer functions and the related approach there. All right, so here are some examples of the modern control. We model like the drones, also like the differential drive mobile robot, and like the autonomous vehicle. These are all based on the nonlinearity, yeah? And we use this kind of nonlinearity to um, to model the system. So sometimes we have to perform like the linearization process, and we may also need to um, define the states of those systems, which could be nonlinear. All right, so about the states itself. So here is what we call the states. So this is the smallest set of variables, also called the state variables, such that the knowledge of these variables at t0, together with knowledge of the input for t greater than or equal t0, completely determines the behavior of the system for t larger than or equal t0. So this is not limited to the physical systems. As we have seen also in control in general, so this kind of approach is also applicable to biological systems, economic systems, social systems, and other kind of systems. Well, as long as they can be modeled with transfer function, they could also be modeled with states. And the state variables that we use here is x1, x2, and others. So basically what we mean by the states are these variables, x1, x2, and others. So Yeah, this is still quite abstract, but so this is the so-called state space equations. So there is x1 dot here, which is a function of x1, x2 until xn. Also, it is a function of u1, u2 until r, and um, it could also be dependent on time. So here we have yeah, the states up to n, yeah, and there is also the input. So this one with u here is the input, and this input is from 1 to r, yeah. And then there is the notion of time. So it could be time dependent, time not time invariant. Yeah. So we have the states x. So these are the states, and we have the input u, and we have time t. On the other hand, so this one is called the state equation. Yeah. So the one with the derivatives of x. Yeah. So these are derived over or with respect to time. Yeah. These are the state equation. Then the next set of equation here is called the output equation, where we have y1 until yn. So these are the output. So there is a set of input. Also, there is a set of output. So input here is x. Sorry, u. X is the state, and y here is the output. And here we have some more functions. So G1, G2 until Gn. So here we have another set of functions just called the output yeah, equations here. So we have the states and we have the input and we have the time. Yeah. So yeah. Um, that's the structure of the state space equations. We have the input and the state together forming what is the function of the yeah, of the state equation, and then we have also the input and the states here also forming the function of output equation. Now, if we draw this, if we represent this with the transfer function, we have x dot is ax plus bu, and y here is cx plus du. Yeah. So the main equations, there are two of these, and if we um, represent this with a block diagram. If we represent this with the block diagram, here there is the feedback here. So this feedback represents that the states here are evolving. So the main process occurs here. As we can see, here is the states x, which is the output of this integral. And then there is the x dot, so this process of differentiation. Well, here x dot is b times u plus a times x. So there is the yeah, change of the states that is affected by the input and the state itself. and x dot here is integrated to obtain x. Yeah, so x here will be multiplied by the matrix or the vector C, which is then added by the multiplication between the input and the matrix or vector D, which then form the output Y. So that's the structure of the state space equations. Again, there are two equations, and here is the comparisons between the transfer function and the state space. So these two are, yeah, very related, closely related. So there is the definition of the transfer function. Here is the output divided by the input, output y divided by the input u. This is g, and um, the state equations are x dot is ax plus bu, and y is cx plus du, and g is c. Yeah, so this c, the matrix or the vector here, times the inverse of S. So S is the operator S, the complex frequency operator. S times I minus A inverse. Yeah. S times I minus A inverse times B plus D. Yeah. So that's the um, calculation of the transfer function. So we have C times S times I minus A. Then we will put an inverse here times B plus D. Yeah. Well, calculation here may be complicated due to inverse. So yeah, perhaps it's not very straightforward, but we can actually trace the differential equations and then um, try to move from the differential equation to the transfer function. So the other approach is to just use MATLAB or other programs. We use TF to SS and SS to TF. So this kind of comments here, we convert the transfer function into state space or state space to transfer function. That's these two can be done quickly. So here is the example. Here we have the state. Yeah, so this matrix, these matrices are representation of state. So we have A here, we have B here, we have C here, we have D. So the SS2TF or the state space to transfer function uses the inputs A, B, C, D, and the numerator and the denominator here would be um, the numerator and the denominator of the transfer function. So for example, for this, we get the transfer function 25. So because there is 25 here, 25s plus 5. So the last number that comes here is the number that corresponds to zero order. Yeah, so 5 times s to the power of 0. And then we go up to the s, and then s square, and then s to the power of 3. And the denominator here is um, s to the power of 3 plus 5s square plus 25s plus 5. Yeah, so that's the um, transfer function that you obtain from this state space representation. One note is that the state space representation here is not unique. So you can have many state space representation which corresponds to the same transfer function. So yeah, this transfer functions state space representation is not only this, but there could be many others. Yeah, actually there could be infinitely many state space representations of this. Right, so when there is no derivative term at the input, it may be easier to set the states x1, x2, and others as the derivative of the output y. So this is the one of the forms of the state space representation. So the third order here, we use like a y triple dot plus a1 times y double dot plus a2 times y dot plus a3 times y. So this is u, and then the state equation here is x1 dot x2 dot x3 dot is yeah 0 1 0 0 0 1 minus a3 minus a2 minus a1. So there is actually a more commonly used structure, and then we have the last row here corresponds to the variable u, and then y here, y is 1 0 0 times x1 x2 x3. So this um, this arrangements of the matrices and vectors here will make the analysis easy. Okay, so that's the transfer function versus state space. Yeah. Um, yeah, this is just one of the representations. Again, there could be many representations of the transfer functions versus state space conversion. So state space could be like this, or could be another state space, depending on the um, methods we used, depending on how we distribute the values among the matrices. So for one transfer functions, again, there could be many state space representation, well, infinitely many even. Yeah. So yeah, please pay attention. All right, so this is one example of the transfer function that we get here. The y over u is given the transfer function like this, 1 over s plus 10 times s square plus 4s plus 16. So this is equal to 1 over s to the 3 plus 14s square plus 56s plus 160. And yeah, of course, this is y over u. Yeah, y over u. And then we can just cross multiply here. So of course we have y times s to the 3 plus 14y s square plus 56 ys, yeah, plus 160 y. So this is equal to u. So y s to the 3, if we then consider this as the differentiations. So yeah, the derivatives, right? So s is corresponding to y dot s square corresponds to y double dot and so on. So here we have the differential equation like this. So y triple dot plus 14 y double dot plus 56 y dot plus 160 y. So this is equal to u. So if we set y to be x1, x2 to be x1 dot, x3 to be x2 dot, we get this y triple dot, this would be x1 triple dot plus 14 um, y double dot, which means also x1 double dot plus 56 x1 dot plus 160 x1. This is u. So this x1 triple dot here is the equivalent of x3, or yeah, if we go slowly here, x1 dot is x2, so this means that this is x2 double dot plus 14 x2 dot, because x2 is x1 dot, and here is 56 x2, yeah, plus 160 x1, so this is equal to u. And also here x2 double dot x2 dot is x3, so this one is x3 dot plus 14 x3 plus 56 x2 plus 160 x1 is u. So of course we can move here, x3 dot is minus 160 x1 minus 56 x2 minus 14 x3. And the representation here is this. So we have a here. So this is x1 dot, yeah, x2 dot, and x3 dot, yeah. And this is a times, of course, x1, x2, and x3, yeah, plus b times u, yeah. So a here is yeah, 0, 1, 0. So this would be multiplied by x1, x2, x3, right? So in this case, x1 dot, the first row here, we have x1 dot is x2. The second row here, we have x2 dot is x3. And then the third row here, we have x3 dot is minus 160, basically this, yeah. Minus 160 x1 minus 56 x2 minus 14 x3 plus u. So sorry, I missed the plus u here. So plus u, this would be like the last row here. Then the output equation is very simple because we have y equals x1. So here we have c is 100 times because y is just cx plus du, but d is actually quadratically used, so we have this as 0. So here y is 100 x1 x2 x3. So obviously y is just x1. Okay, so that's the relationship between several variables in the system. So yeah, y we have x as the y as the output, x as the state, u as the input, and so on. So again, this is only one of the state space representations. There could be many others. Yeah. For example, if we set y equals not x1, but let's say 2x1, then the entire representation will be changed. Yeah. Okay, so in this example, we see that um, there is like a polynomial for the numerator, and this one could be handled a little bit differently from the other uh, problem. This one with the polynomial numerator, we can set the output here to be the polynomial, so to be related to with the polynomial, so x1 plus 2x2. Then we have x2 is x1 dot. Yeah, and this one state space representation we can see here is that a is 0, 1, minus 9, minus 7. B is 0, 1, and C is 1, 2, and D is 0. Yeah. So if we try to go from here to here, it's quite tricky actually, but if we try to prove this, go the other way around, so from here to here, um, we can get so here is minus 9, so x2 dot this one would be minus 9 x1 minus 7 x2 and then this one would be plus u, right? And yeah, here x1 dot is x2 and y is x1 plus 2 x2. Yeah. So if we look at this, we try to convert everything here in terms of x1 and x2, and then in terms of y, sorry. So in terms of y, we try to convert them to y. In this case, this one is x2 dot here. Yeah, we can convert this to x1. Yeah, and x2 here can also be converted to x1. So because the first equation here states that x1 dot is x2. Yeah, so x1 dot is x2, therefore this one it could be like minus 7 x1 dot, right? And then this one is x1 double dot, and then y dot here is x1 dot plus 2 x2 dot, and then um, yeah, because x1 dot is x2 dot, and we can also do y dot x1 dot plus 2 x2 dot. So we then move this x2 dot minus 9. Yeah, so this entire term. So here is 2 times minus 9 x1 minus 7 x2 plus u. Yeah. Then this y dot here is x1 dot plus or minus x1 dot minus 19 x1 minus 14 x2 plus 2u. And from here, we can get that u here is minus 9 x1 minus 7, sorry, u is x2 dot plus 9 x1 plus 7 x2. Then we get that x1 dot here, this could be moved from this equation to the following equation. Okay, so then the next example here would be this matrices. So the one here we have is A, B, C, and D. So the previous one is a little bit tricky because we have polynomial, but now we do not have polynomial anymore. So the one that we have here is A is 0, 1, 0, 0, 0, 1, minus 5, minus 25, minus 5, and then B is 0, 25, minus 120, and C is 1, 0, 0, D is 0, and by, so this is, we have 3 times 3 matrix, so the dimension is higher than the previous one. So then we get minus 5. So x1 dot is clearly x2. x2 dot is clearly x3. And then x3 dot is minus 5 x1 plus or minus 25 x2 minus 5 x3. So x1 dot is x2, then x2 dot is x3, then x3 dot is minus 5 x1 minus 25 x2 minus 5 x3. And no, sorry, one more thing is that this is no not only x3 but is x3 plus 25 u. Yeah. So then we get this x3 dot is minus 5x1 and so on. And to obtain the transfer function, we need to work with y. So y is x1 clearly, then y dot is x2 because yeah, y is x1 and y dot is x2. So then x3 dot, yeah, we will keep it as it is for now. So this is same as minus 5 y minus 25 x2. Here is y dot minus 5 x3. So x3 is x2 dot minus 25 u x2 dot minus 25 u and this is x3 dot. So x3 dot. Okay, so let's finish this up first. So this is minus 5y minus 25 y dot minus 5. So x2, yeah, x2 is y dot, therefore x2 dot is y double dot. So this one is 5 times y double dot minus 25u. So x3, so x3 from the second equation here, x3 is x2 dot minus 25u. Then x3 dot is x2 double dot minus 25 u dot. So this one is x2. So what is x2, right? So x2 is y dot, therefore x2 double dot is y triple dot. So therefore this one we have y triple dot minus 25 u dot. So minus 25 u dot. Yeah. And then yeah, we can group this together. So y triple dot here plus 5y plus 25y dot plus 5y double dot. So y triple dot plus 5y double dot plus 25y dot plus 5y is 25. Okay, so this is 25 u dot plus 125 u. Yeah. Okay, yeah, sorry, it seems that I missed something here. Okay, sorry, I missed the minus 120. So, uh, complete this, we need minus 120u, which also here, which also here. So then we have 25u dot plus 5 because minus 120. Okay. So then the representation, transfer function representation is as this, where the numerator is 25 s u plus 5u, and then the denominator is s to the power of 3 plus 5s square plus 25s plus 5. Yeah, so 5 here and 5 here happens to be the same. So that's one example. Another example, how to convert the state space to transfer function. Yeah. So the previous ones to convert transfer function to state space. This one is to convert from state space to transfer function. Right now, for the more concrete example, we have the model, the mechanical mass spring damper model. So M times Y double dot plus B times Y dot plus K times Y is U. And if we set that the states x1 is y and x2 is y dot, therefore x1 is x2 dot, sorry, x1 dot is x2. Yeah. So x2 is x1 dot. So we get this c is yeah, just 1 0 because y is x1, so doesn't need to use x2. Then yeah, y dot here is x2, which means that the first row here is 0 1 because this will be multiplied by x1 and x2. So then yeah, the matrices here will follow. So because we define y as x1, and we define that x1 dot is x2, therefore we have m x2 dot plus b y dot is y dot here is x2 minus plus b x2 plus k x1 is u. So x2 dot is equal to minus k over m x1 minus b over m x2 plus 1 over mu. So we can arrange this with the matrix here like this. So the first column would be minus k over m, the second column would be minus b over m, plus 1 over m here would be the second row of the vector b. So yeah, that's the state space representation of this. So A, B, C, and D are all obtained D is commonly set to be 0. Then the uh, block diagram of this mass spring damper model could be written or could be drawn as this, which means that this system could be considered a closed loop system if we set the um, states as the um, a variable that becomes the output of some of the block diagrams. All right, so that's about state space representation. So here is the application, which is the feedback control. So one of these um, type of control that uses state space representation. So this one of the control method here is called pole placement. So we have the pole placement here with K as the feedback gain. So unlike the PID controller that we are discussing previously, which uses the um, feed forward control, this one uses the feedback control. So the K here, the gain is the the gain of the controller. So we no longer use this. For this state space based control, we do not use proportional gain, integral gain, or others. We use like the feedback gain here that is using the state as the input. And then the output here would be compared with the reference to produce the error signal. Okay, then the next here is about the nonlinear control. So previously, what we have studied is the analytical methods such as the analytical PID controller. This one is for linear systems. And now the next question is, how can we deal with nonlinear systems? So as we as I have mentioned before, so many systems are nonlinear and they cannot be perfectly controlled with the linear model unless we cannot unless we do not like a guarantee stability or performance. So of course we can control this, but it's more of a trial and error method, but it's not a theoretically not theoretically guaranteed that we can perform the control in this linear model. So one method that we use here is called linearization. So this linearization is basically approximation of a nonlinear system that is valid in a small region around an operating point. So the curve here is a nonlinear curve. So we have the nonlinear function y is x squared. So there is a point called operating point. So this operating point here is the point in where the um, system is working, right? So if we are talking about, let's say, the drone, and we want to perform like the automatic takeoff or automatic landing, then the the angle, the linearization point here is for the angle to be, let's say, 0, because we expect them to operate, um, yeah, mostly at time 0. Sorry, at angle 0. Yeah, so um, yeah, we do not expect them to operate at like some extreme angle, for example. So this curve here is the same as this line. Well, of course, it's not the same, but it's the same if we look only at point 1, yeah, 1, and the region around that. So this one region um, represented by the green squares, uh, green box here, that's like the linearization region. So to perform linearization, here we could use Taylor series at point x 0, or this is the operating point. So for using the Taylor series, we form the function, the nonlinear function, to be the fx0 plus the derivative of f at x0 times x minus x0. For example, if we have x squared, then yeah, we have x squared, which is our main nonlinear function. So at 1 comma 1, so here fx is fx 0, which is 1, because if x0 is 1, then the fx0 is also 1, because it's 1 square. So this one is 1, and then we have the derivative of this, derivative of f, so derivative of x squared, which is 2x, 2x given x is 1, then it's times x minus 1, so this one is 1 plus 2 times x minus 1, um, then we have like a 2x minus 2 plus 1, so we have 2x minus 1. Yeah, so that's the linearization of this x squared, yeah, which is a linear, well, a straight line with the gradient 2, and the um, yeah, the offset minus 1. Okay, some simple example here is that we linearize y is x squared around x equals 10. So dy dx is 2x y. Yeah, of course, we differentiate this with respect to x. Then y is 100. How do we get 100? Because it's at 10. So if we look at the previous slide, it's fx0. So x0 is 10. So then this is fx0, yeah, which is 100, right? Because it's 10 square. Then the derivative of this is 2x. So 2x, um, yeah, so this is the linearization, 2x, where x is 10. So this would be 20 times x minus 10. Yeah, so we have this. And then it's 20x yeah, 20x minus 100. So 20x plus 100 minus 200. So 20x minus 100. So that's the linear equation or the straight line that is a result of the linearization of this y equals x squared. So the next example here is that z, this is a two-dimensional linearization. So z is x squared plus 4xy plus 6y squared in this region. So from x, for x from 8 to 10, y from 2 to 4. So this is yeah, fxy, so meaning that it's a function of x and y. So here is x squared, yeah, of course, plus 4xy plus 6y squared. So z here, the linearization would be yeah, so fxy here would be like this. So it's the result of f of x bar. X bar is the average of this, y bar is the average of this. So this is the derivative of f with respect to x. So this would be 2x plus 4y plus 6, no, sorry, 12. Yeah. So this would be 12y. Yeah, so this one x is x bar. So then we get this equals 9. The x bar here, the average point here is 9. Then y bar here, the average point is 3. So the x minus 9, then y minus 3. So we plug in the value of this. So here we get, yeah, 2 times, yeah, we plug in the value here, 2 times 9 plus 4 times 3, yeah, plus 12 times 3, yeah, so 18, 12, 30, yeah. So K1, here we have K2. So K1 is 18 plus 12 plus 36, so 66. And K2 follows with the same method. And then, yeah, we get this f x bar y bar. Of course we just plug in the values here. So this, for example, would be 81. So because 9 square, then the next one is 4 times 3, 12. Sorry, 4 times 9, 36. 36 times 3, 108. And then here 6y square. Y square is yeah, 9. 9 times 6 is 54. So that's the z bar. Then we arrive to this equation, which is the linear yeah, linear approximation of this nonlinear curve, yeah, two-dimensional. with two variables, three-dimensional curve. All right, so lastly, we have the linearization of systems near equilibrium points. So our equilibrium point here is x dot um, is 0. So if we linearize the differential equation, fx is x dot is 2x square near the equilibrium point, then we have the solution of this is that we have 2x square, therefore 2x square here would be x dot, and we select the 2x square here, x dot to be 0, which means automatically x becomes 0. Then the differentiation of this to x square, it results in for x, then it's the derivative of fx, with respect to x. So this would be x dot, which is also 0. So near the equilibrium point, x dot is 0. Here the function has the approximation of 0. So that's the linearization of this of the system near the equilibrium point, x dot x is 0. All right, so that's for the topic we discussed today about the state space representation and the linearization. So yeah, we will continue with a quiz and some post test on Thursday. Yeah, so Thursday 4th, June 4th, and yeah, after that we will continue with the final exam next week. Sorry, I mean, yeah, the week, the Thursday 11th. Yeah, Thursday 11th. Yeah, so don't forget to work on the short exercise, and then work on the assignments. So assignment 8, I think you can work on. Also assignment 7. So there's new assignment 7 and 8. Whether or not we need assignment 9 would be discussed further next week. We will see how it goes. Yeah, so let me open the classroom quickly. Okay, so this is assignment 6. Sorry, I think 6 is done, right? So 7 and 8. So these two you need to work on. Well, 8 I will upload after this. Then yeah, 9 I think we will see. Maybe we don't need 9. Maybe we do. We will see next week. Okay, so I think that's it, and I will see you Thursday the 4th, where we will have a quiz. Yeah, so please prepare for that. Although you can just open your books, notes, but not electronic devices. So yeah, it would be quite short, and when we will discuss, and then we will see the um, see the um, result, or we can discuss the quiz, and we will see how we continue from there. Okay, thank you, and I will see you next time.